Okay. Well, welcome everybody. Happy Friday. Hope everybody's comfortable. So, I have two things on my to-do list today. First of all, I do want to finish off Chapter 4. Make sure, because that's the last chapter that's covered on the test on Tuesday. I want to make sure you're all set for the next time we meet, which will be Tuesday evening, actually, because there's no class on Monday. And the other thing on my to-do list is I really do want to get going on Chapter 5 stuff, which you actually be tested on until November 21st in Test 2. So if you'll bear with me, what I would like to do is do those in opposite order. So I'm going to spend the first 20 minutes or so talking a little ahead of time. And then we'll get down to the more stressful kind of urgent business of Chapter 4. Are we okay with that? Rhetorical question there, but yeah, so basically motion and a circular path, how does that work? And the answer to this whole question is turning at a constant speed, acceleration. Does it have an acceleration value in meters per second squared? The answer to that question is yes, and we'll get a little bit into that if there's time. And then I'll move on. And there you can see, I think this is vertical circular motion where you've got gravity as a constant force, and then you've got this net force is kind of the white arrow there, I think, and then there's some sort of variable red force, like a tension force or something. Okay, but let's look at a couple of things from above, first of all. So this demo doesn't have a video to it, but the basic idea here is that if I take a bowling ball and kind of roll it along, it goes at a straight line. And if I want to turn it as it's moving, so maybe I need a bowler actually. Does anyone want to anyone in the front row want to come up and bowl this thing towards me? Or You're a little too crammed in, sorry. I think we'll take bowling. So just bowl that kind of towards me, and then what I want to do is try to turn it and get it, so you need to give it some good speed. Yeah, good speed. So if I want to turn it, I have to kind of hit it towards the center of motion. Thank you. Okay. So I don't know if you were seeing, but what I want to do, I'll show it on the screen, I guess, is if it's moving kind of sideways, so you can see here, I think, Bowen sent the ball this direction. I had to hit it on its side to make it turn. Sort of makes sense, right? Here, if it's going from top to bottom, I'm trying to make it turn left. And then I have to continuously tap it. And the only thing that works to get it to go in a circular motion is to tap it towards the center of the desired circular path. You're always turning. And if you wanted to look at it in terms of the force diagram, this is actually the side view. This is maybe, sometimes you do a couple of diagrams. You do like the sketch and translate, and then you do the simplify and diagram step. The way I think of those two steps is that the sketch and translate sketch is when I'm just kind of organizing my thoughts and trying to picture what's going on. And then the simplify and diagram, force diagram, is where I'm really trying to put letters on things and get my Newton's second law equations set up. So this is like a top view to remind me what's happening. And then I actually, for the force diagram, I do the side view. And there's a normal force of the floor on the ball, the force of the earth on the ball, which is the mass of the ball times g all the time. I don't have an equation for normal force. And then there's the force of the mallet, this rubber mallet that I was trying to hit it with on the ball, which I'm smacking it. And that's what gives it an unbalanced force towards the center of the circular path. And then I guess there's another side view. This is the side view over here. This is the side view over here, where I'm actually hitting it on the other side. Now the force of the mallet's on the other side, but since the ball is way over here, that's this force diagram. Again, force of the mallet is towards the center of circular motion. Okay, so now I need another volunteer. Somebody who has a heavy backpack. You have a heavy backpack? I want you to do this. We could do a video, or you could just swing it around. So can you imagine just sort of swinging around in a horizontal circle, please? Yeah, like that. Maybe a few times. Nice. Okay. And which way are you pulling? You're pulling, right? Okay. Towards yourself. Okay. Awesome. Thank you very much. Really good. Thanks to both of you. But you can do a force diagram for that as well. Your arms are pulling the bag, and there was a little bit of an angle I could see as well. And so force of you on your bag is kind of up and towards the center a little. And the way I would draw, I had some notes for that. I'll try to do that is we've got, I guess this is like, I don't know, like a tension force or something like that. And I would say that the forces, some of the forces in the y direction should equal 0 because the bag's not accelerating up or down. But you've got in this sort of r direction, if this is the r direction, the sum of the forces in the r direction is greater than 0. You're pulling it in the r direction. So there's like a net force in the plus r direction. If r is this axis towards the left, okay, for this particular point in the path. So it's a little weird. You've got y, which is just up, but now you've got the r direction, which is always changing and is always towards the center of the circular path. So from these experiments are what we might those sort of observation experiments, we might say, when an object's moving in a circle, the sum of all the forces exerted on it by other objects is directed towards the center of the circle. And you can test this, I guess. What if you remove the inward forces all of a sudden? Does the object cease to go on a circular path? So we can kind of try to do it as a top hat question, I guess. A ball, so this is a bit difficult to picture, but what you're looking at is the view from above. So like bird's eye view. So there's no gravity in this picture. Gravity would be into the frame. So if you imagine that. A ball rolls on a frictionless track on a horizontal table, and the track is curved in a 3/4 circle. So you've got some walls on the edge of the track or something that guide the ball in a circular path, or 3/4 of a circle. And then the ball emerges, so it starts here, goes down like that, follows around a circular path, and when it emerges at the top here, which of these 5 dashed lines most closely represents the path of the ball when it emerges from the track? We've got a demo set up to try it as well. So think about it. Check your neighbor. What does your neighbor think? See what people are saying. Then we could try it. I just want to see what the vote is actually first, and then let's swap it. Okay, so the vote says 90%. So let's just try to test it, I guess. Okay. As you can see, we've got a little flat table here. So I roll a ball. It goes kind of in a straight line, no matter which way I put it. But if I start it in a circular path and the force goes away, as soon as the force goes away, whatever its most recent velocity was, it's just going to continue with that velocity in a straight line, I think. You can sort of see it. I don't know if we can sort of have a line to guide the eye there. Whoop. It goes along, straight line. It doesn't remember that it was going in a curved path after you take away the force of that wall. So C was exactly right. I like it. Seem good? And then can I just go top one. Like that. So I liked it. Okay. Basically, c is the tangential velocity at the moment that the force goes away, and so it stops accelerating. There's no horizontal net force anymore. I think. Maybe I should stop it there. I could go on and on because I love all this Chapter 5 stuff, but I'm feeling a bit of tension in the room about the test coming up. So want to start talking about that a little? So, don't forget, you got to come Tuesday evening, 6 o'clock. So 6:10 is when the test actually starts. It's based on chapters 1 through 4, so not this circular motion stuff. Well, I think it's very cool, important stuff. And there's 10 multiple choice questions worth 2 points each for just right or wrong. So instead of 1 point, it's 2 points. And then one written answer question that's worth 8 points. So I just sort of wanted the weighting to be 20 to 8. And keep in mind, I'm going to post this, I think April might be posting it right after this class, that the room assignment might not be exactly the same room as you went to for the mini test based on your last name. We rearranged the rooms a little bit because they've done a big renovation in room 300 that only allows fewer students, I think. So these are actual last names, and you have to figure out sort of where your name fits A through Gia, where Gia is the last name, but Jiang goes into EX200. So the J's have been flipped around. So make sure you at least know where you're supposed to go based on the alphabet. I find myself often singing that song, A, B, C, D, E, F, G, H, I, J, K. Okay. Don't forget to bring your T card. Anybody know who Aubrey Graham is? Huh? I don't know if he went to U of T. Okay. Calculator, rate sheet, something to write with, obviously. I posted the first page just so you can sort of see what the instructions are. It's under the module. It's the same place I'm going to post the solutions. These are the same exact kind of rules that you had for the mini-term test and for every term test and every final exam. It's an 80-minute test, so it'll start at 6:10, end at 7:30. You got to stop writing. Okay. Some hints, probably good not to be late. You got to take into account things like the TTC. You don't want to be stuck on a subway while everyone else is writing the test. For me personally, what I would always do when I sat down to a test is I'd spend the first 2 or 3 minutes just reading through the whole test without answering anything. You've got an hour and a half almost, and so you can definitely spend 5-10 minutes at the beginning reading the test, skimming, looking for the easy problems. And before you really answer stuff, it's important to read the question carefully. I kind of even almost dictate the question out in my head silently. One of the most common mistakes on any test really is misreading the question. If you have a non-smart watch, it's good to have that, I think, because maybe it might be hard to see a clock from where you're sitting. So I think it's a good investment to have a $10 watch, you know, from Spadina or something like that, or $15 from Shoppers Drug Mart that has the time, so you can manage your time. You got 11 problems over 80 minutes. It's kind of an average of about 7 minutes per problem. You can't have your phone, right, or a smartwatch. So you got to get used to using your calculator and your watch to tell what's going on. What time is it? And all these calculations. You don't want to be doing arithmetic on a test either, right? Okay. And I can do just more stuff. You are allowed a paper dictionary. It could be a translation dictionary between your first language and English. The invigilator might flip through it to make sure there's no extra physicsy stuff written there. Just write that on your aid sheet. Your bag with your phone and stuff should be either at the edge of the room, or you can put it kind of under your chair as long as you can't see your phone. That's the main thing, or your smartwatch. I guess I wanted to just do a quick survey and then ask if you guys have any questions. This one's not for marks. But how you kind of wondering what people are feeling like? Is it like A, confident, and then in your confidence level of C is like, meh. This is a good time. If you have any general questions you think might be of interest to the whole class. Yep. Can I just, whoop, thank you.
Are we allowed an H sheet for this test?
Aid sheet, yes. Okay. So I'm not going to give you any equations. You can see the first page where I give you things like G and conversion between centimeters and kilometers or something like that. But I'm not going to give you any of those equations. So you need an aid sheet with all the equations written on it. And you can write anything you want. Anybody else? Yes, you ready? Yes, question?
I have a question. So is the difficulty level, is it going to be the same as the mini-term test?
Yeah, difficulty level is similar to the mini-term test or the problem sets or something like that.
Okay.
Yep, exactly.
Oh, she wants to ask.
Sure, question?
What exactly do we need to know from the labs?
Well, yeah, you should have some familiarity with what was going on in the labs with motion. You guys had the two experiments that you did in the lab, you should have some familiarity with it. There's not going to be like an uncertainty analysis question on this test, but there is going to be chapter 1 through 4 stuff. So the pulleys and forces and things like that are going to be important. Yes, question. Ready? Just watch the laptops. Love it.
So in class, we do a lot of problems where our answer isn't a number and it's just like in terms of variables.
Yeah.
Are the free response questions on this test and all like future finals and term tests gonna be like where the answer is a numerical value with like units on it, or like a formula that we create ourselves?
Yeah, that's a good question. So there's numberless problems where you have to answer like the actual variables. That might show up in the test, yeah. I think they're mostly numbered problems, and then some conceptual questions, and there might be something where you you have to just show an equation, and so there'll be like 5 equations, and only one of them would be correct, or 5 mathy things. Let's do one more. I see a hand up there, and then we'll look at the results of this survey. Could you, ready? Catch? Pass it back, thank you.
2 things. First, we're going to need to bring the aid sheet to have like all the equations, but any like values or numbers, like gravity, those are all going to be on the test?
Yeah, any values that I think you would need, such as the conversion from centimeters to meters, I'll put it on there.
Okay, also, are we going to need to calculate like the margin of error for anything?
Yeah, no, so there won't be any of these uncertainty analysis stuff that's from the practicals. That's not going to be on the term tests coming up.
Cool.
I think it's good to have it in the class, but I can just tell you it's not on this test. Great. Okay. Should we look at overall feelings, and then I'll come back? I'm a little curious about this myself. Ooh, well, it's all over the place, isn't it? Okay. Very few people in the middle. It's like a histogram that has 2 bumps on it, up, down, up, down. Let me do an example that I was going to do last class, actually, since we're here. This was one of the last slides I showed on Wednesday, which was looking at this is a table from your textbook, various coefficients of kinetic and static friction between 2 surfaces. So I just wanted to know, sometimes you see people publish for cars how fast they can go, like how much time it takes for them to go from 0 to 100 kilometers per hour. So is it possible just from this table to figure out what's the shortest possible time if you're just about to slip? Because I think if you step on the gas too much, you could screech your tires, and then your tires are slipping, and so you only have kinetic friction. It's only if your tires are rolling without slipping that you have this forward static friction. So here it is. I'm going to define the system as a car. Oh, thank you. I'm glad you guys are yelling at me. So anyway, I just spent a lot of time talking about the slide you couldn't see because I was out to lunch. We need to give tomatoes to the front row or something like. Not tomatoes, tennis balls. Remember this table? Idea is, can I use this table to figure out what's the shortest amount of time you can accelerate from 0 to 100 kilometers? Define the system. This is the car. So let's do a little sketch. Here's a car. And we can draw, I guess, our little dashed line around it. So any external forces on the car I have to put on the force diagram. I guess I'll say the car mass is m. V0 is 0. And V final is 100 kilometers per hour. So unfortunately, that's not an SI unit. So I think probably a good idea is to convert this to meters per second. I don't really like it when things are in non-SI units. So sometimes, so I got kilometers per hour. How am I going to convert that? Well, I can do 1,000 meters is 1 kilometer. And then I can, multiply by also, I know I think there's 60 minutes is 1 hour, and also 60 seconds is 1 minute. Minute. So the way that works is the kilometer cancels kilometer, hour cancels hour, minute cancels minute, and the only thing that's left is meters and seconds. So I just take that 100, times it by 1,000, then I divide it by 60, and then I divide it by 60, and I get 27.8 meters per second. Okay, so then what I want to do, let's define plus y is up, x is to the right. Let's do force diagram. There's the normal force of the surface on the car. There's the gravity force of the earth. And then there's the static friction. So what I'm going to do is I'm going to set that to Fs max to get the shortest possible amount of time. And I'm going to set the acceleration to be towards the right here. And I'm also going to assume that it's rubber tire on dry concrete. Rubber tire on dry concrete. So if we go back to that table in your book, it lists mu sub s. It was 1.0. So now I can kind of represent mathematically. So the sum of all the forces in the y direction is mass times the acceleration in the y direction, which in this case is 0 because it's not accelerating up or down. And that's going to be equal to the normal force minus mg. And so from that, I think you can solve out that n equals mg. And then the sum of all the forces in the x direction is the mass times the acceleration in the x direction, which is what we're kind of trying to find here, I guess. And that's going to be just Fs max, which there's an equation for that, mu sub s times n. And luckily we have n from the y balance equation. So I think you can solve for a sub x. It's going to be the sum of all the forces in the x direction divided by the mass. So it's going to be mu sub s times m times g divided by m. M's cancel. And then you get a sub x is equal to mu sub s times g. And then, so that's actually equal to 1.0 times 9.8. So it's 9.8 meters per second squared. And so at some point then I'm going to use V is equal to V0 plus A sub x times t. Put x's and all that stuff, and solve for t. Because t is what we care about, and we have the final velocity. So t is equal to v final divided by g, I guess. So it's 27.8 meters per second divided by 9.8 meters per second squared. And it ends up in seconds to be 2.8 seconds. Which is a little weird, because I went on the internet and I found that some cars do it even faster than that. I think the record I saw is 2.3 seconds. So I don't understand that exactly. I think what might happen, so I actually, my mom once dated a guy who was a race car driver, and he came one time pulling into the driveway, and there was all these leaves stuck to his tires, and because it was fall, I guess. And I thought, why is that happening? I think that the tires on some of these race cars are kind of sticky. So you can actually have coefficient of static friction that's greater than 1, because it's kind of sticking to the floor, so that they can really accelerate really fast. So maybe this 1.0 is a little low. We could have it's possible maybe in principle to have a static friction force that's greater than the normal force. Anyway, it's right order of magnitude. Should we do another question? This was something else I wanted to try. Well, not try, but think about it. So I have a great pizza dough recipe that requires a kilogram of flour. And you don't want to put too much flour in there, or else it's kind of really sticky, and then you get this like flat pizza dough. And you don't want to put too much, or it can be too dry. And so you want to have just the right amount of flour. And so I have a spring scale, and I pour the flour in there till it goes up to a certain limit. So let's imagine that I was doing that. I was about to make some pizza, but I was on the elevator and accelerating upwards at 1.5 meters per second squared, trying to measure. And I pour the flour until I see the dial go up to my favorite little value. What's going to happen to my pizza? Not enough flour? Too much flour? Or it should be okay? I'll let you guys think about that. Think, pair, share? Okay. So please answer this one and give your best guess, and then I'll try to explain what I'm thinking here. Okay. And then we've got another one with an actual demo. Not enough flour. That's what I liked as well. So my reasoning for that was I thought, okay, for any given amount of mass, if it's accelerating upward, the spring must be pushing with a greater force than the gravity pulls it downwards. Okay? So what's going to happen to the dial is that it's always going to be reading high. So if I start pouring flour in there, it's going to reach, and I'm going to say, oh, that's enough, before it's really enough. Does that make sense? If it reads 1 kilogram on the scale, it's not really going to be 1 kilogram. And, the moral of the story is don't try to cook in an elevator, but a couple of the questions just from the floor I was answering, which is that there's not going to be uncertainty calculations on the test. If you need things like these coefficients of static friction or kinetic friction, those are numbers which I don't expect you to put in your aid sheet. I would put that on the test itself, maybe in the question or something. It's the equations you need on your aid sheet mostly. Okay. People want to do another? Let's think about this. So actually, I have a pan balance, right? Do I hit aux plate? You guys know what a pan balance is? So what I want to do here is, the idea here is that there's a pivot in the middle. And if I put mass on one side, and if I balance it with another mass, this is sort of the old way of comparing two masses. Whoop. Okay, so now there's 100 grams on both sides. If I take some off, it goes up like that. Put it on. If it's exactly right, then they balance out. So you've got sort of a pivot with two forces. That's called a pan balance. And the question is, I'll send to your top hat right now. You are attempting to pour, again, a kilogram of flour, and you have a pan balance. So I have something that I know is a mass of a kilogram on one side of my pan balance, but I'm on an elevator once again, accelerating upwards at 1.5 meters per second squared. So, is it going to work or not? Am I going to get too much flour, not enough flour, or the correct amount? Should we see what people are saying here? Survey says 84% like the correct amount. I guess, again, my reasoning here is now we're comparing actual masses. That's what a pan balance does. It's comparing the mass on either side. You could have just gravity pulling down. There's normal force pushing up. But since they're both accelerating upwards, I think you're just going to keep pouring flour until there's the same amount of mass on both sides. Do you still have a question, or you're okay? Okay. I was just a little ahead of you. Too late. All right. Everybody's good. So let me go through maybe the chapter 4 problem-solving sort of strategy that comes up, because there's a good chance that your written problem on the test on Tuesday is going to be, a chapter 4 type thing, and then we'll do an example. We got time for that. Okay. So it goes like this. Sketch and translate is sort of the first step I like to do. That's where I'm making a sketch, just a rough sketch of the process, and I have to choose a system. And sometimes this is kind of a tricky part, and you may have to leave time to kind of try different systems. Because sometimes you'll choose a system and it doesn't really work out. You end up with kind of a dead end. And I think when we had that one problem set where there was 3 books stacked in an elevator and it was going up, the question was, what was the normal force of the bottom book on the middle book? If you choose the system as the middle book, it didn't really work because there was a normal force from the top book squishing it and the normal force of the bottom book supporting it. And both of those were unknowns, and so it wasn't possible to solve the problem very quickly doing it that way. You'd have to do another system, which would be the top book, and solve it all out. Or you could do another trick, which is define both the top and middle book as being your system. You also have to define a coordinate system, show like what your plus y and your plus x is, and try in that sketch to put on your unknowns and the quantity of interest. So something equals a question mark is a thing that you've been asked for. I don't know what the normal force is on this, but I'm asked to find it, so that's important. At this point is when you try, thinking if there's any way to simplify things. And main stage here is that you're probably going to have to draw a force diagram. The reason you draw a force diagram is so that you can sort out what your forces are for Newton's second law. This whole part of the course, the first half of the course, it's all about Newton's second law. The sum of all the forces acting on the object equals the mass of the object times the acceleration of the object. That's how you find the normal force. That's how you find the static friction. That's how you find the tension. Because you don't know those things until you solve out Newton's second law. And you can't really figure out Newton's second law until you draw a force diagram. And usually the acceleration is something that's you kind of know because it's on an elevator or something like that, and you work backwards to find what these forces are. Make sure that your diagram looks all right. And then at that point, you use the Newton's second law. And it always kind of comes out to be, there's a few different ways of writing it, but the sum of all the forces in the x direction equals the mass times the acceleration in the x direction, and the sum of all the forces in the y direction equals the mass times the acceleration in the y direction. That's it. And sometimes the acceleration is 0 because it's going constant velocity. That's even easier because then you know that the sum of all the forces has to equal 0. sometimes you define your y-axis so that the acceleration is only in x, and there's no a sub y. Then you can balance your y components of your forces. Okay. And then you solve it out, put in your numbers. I tend to put in the numbers last. And it's always good to kind of, at the end, do a sanity check to make sure it sort of looks all right. Want to do an actual example? 2 blocks. Masses M1 is 1.0 kilograms, and M2 is 2.0 kilograms. So the point here, I think, is that M2 is greater than M1. So my feeling is that the whole thing's probably going to accelerate kind of this way, right? It says it hangs at the ends of a string that passes over a very light pulley with low friction bearings. When the system is released from rest at a time t0, the bottom of mass 2 is 0.25 meters above the floor. At what time does M2 hit the floor? So this D is equal to 0.25 meters. And I'm going to assume here, which sort of makes sense, since M2 is the larger one, it's going to go down, right? So M2 hits the floor. I'm also going to assume that it hits the floor before M1 hits the pulley, I guess. Or else we're not going to be able to solve this. Sometimes it's okay to make a few assumptions. There's going to be an upward tension force on both of these. So what I like to do in this case is just make 2 systems, one for M1, one for M2. That's okay. Same tension on both. And so what will happen here is that M2 will accelerate down, and M1 will accelerate up. And what we need, I think here, 2 separate force diagrams. Sort of sorting out my thoughts here. And then what we're going to do is we're going to find the time for M2 to travel. Once we have its acceleration, we know it was released from rest. D is equal to 0.25 meters. So, what I'm going to do is kind of split it up here. I'll do my M1 force diagram and my M2 force diagram. So for M1, they're both actually very similar, right? You've got tension acting up and the force of gravity acting down. So I can draw that here as well. Tension acting up and the force of gravity acting down. So they're very simple looking diagrams, but M1g is the force of gravity on M1, and M2g is the force of gravity on M2. And it's a little weird because the other thing I like to do for a force diagram is I like to draw the acceleration somewhere nearby, and its direction. So M1 is the one that's going up, so the acceleration is upwards. And M2, the acceleration is going downwards. So it's the same tension in both, but different forces of gravity, and that's why one of them has an unbalanced force in the upward direction, and the other one, second one, has unbalanced force in the downward direction. So I think what I'll do here, this might seem a little strange, but let's define plus x is up for this one, and we'll define plus x is down for this one, so that they both have positive acceleration. And then what we can do in the represent mathematically for M1, it's just the forces in the that x direction is equal to the mass 1 times the acceleration in the x direction. So the sum of all the forces tension minus M1g equals M1 times a sub x. I think it's pretty important to have the difference between the sum of all the forces is mass times acceleration. That's Newton's second law, but how things move. And then the force of gravity is the mass times g. where g is this 9.8. It's sort of a whole different thing, although those equations look really similar. For m2, you've got the sum of all the forces in its x direction is equal to its mass times its acceleration. And the sum of all the forces in this case is m2g minus tension. And so these, what you've got now is two equations and two unknowns. This is the same tension and the same value of ax for both. Because since they're attached, if one's moving up, one's moving down the same amount in the same amount of time. So they have the same velocity and they'll have the same acceleration at any moment, except in opposite directions, because they're attached. So our strategy here is I'm going to do, let's eliminate t, the thing we don't care about, t, and solve for a. And so I can use this equation to get t is equal to m1 times a plus m1 times g. And then this equation I can also solve to get t is equal to m2 times g minus m2 times a. And then what I could do is just set t equals t. I mean, there's a few ways of eliminating, but if you do t equals t, then you get m1 times a plus m1 times g is equal to m2 times g minus m2 times a. And then I want to gather all the terms with a on one side of the equation, so I can solve for it. m1 times a plus m2 times a is equal to m2 times g minus m1 times g. Then I can pull the a out of this equation. m1 plus m2 is equal to, I can pull the g out of this equation, I guess, m2 minus m1. And so the a, acceleration, is g times the difference in the masses divided by the sum of the masses. So, so what we had here, don't forget, you've got m2. It's going down some distance. D is equal to 0.25 meters. And here's the floor. So for this falling, this is the acceleration of m2. We know that v0 is 0. It's released from rest. We know d, and we know a sub x. And we need t, the time. And the thing we don't care about, so this is a kinematics problem, so about, I think, v final. So the equation I'm going to use is that that x distance is v0 t plus 1/2 a times t squared. And you can, this is 0, so you can solve up for t, is t is equal to the square root of d, 2 times d divided by a sub x. And then, so if you plug in your equation for a sub x, you got 2 times d divided by g times m1 plus m2 divided by m2 minus m1, all square root. So plugging in the numbers for that, I've got t is equal to the square root of 2 times 0.25 meters divided by 9.8 times 2 plus 1 divided by 2 minus 1. All in SI units. Plugging that into my calculator, I got 0.39 seconds. Okay. So I'll post that up. And I will stand around for another half an hour here, but just a couple more hints for Tuesday night when I see you next. At least 5 of the multiple choice questions will be conceptual questions with no calculations needed. You do these in less than 2 minutes. If you do start a longer problem and you find yourself spending more than 10 minutes on it, You might want to make a mark at the edge of the paper and come back to it after you've solved the easier problems. Don't waste your time on one question, really all your time. If you're in a hurry, you can make little mistakes. I always like to bring a banana, so halfway through the test, I can have a snack. I also feel it's probably not productive to leave a test early. You know, just keep going. You got the 80 minutes, might as well use the 80 minutes. And if you celebrate Thanksgiving, happy Thanksgiving. And I'll see you on Monday, or see you on Tuesday night, and then on Wednesday.